Here's part 3 of chapter 6.2. We're talking about binomial probability distributions, random variables, and probabilities with that. And so just like in previous sections in chapter 6, we calculated the mean and standard deviation. There was a formula for that, but we used StatCrunch on a custom calculator because that was a probability distribution with a random variable that was not binomial. In this case, we have a binomial random variable. And so recognizing that then leads us to a different formula because it's a different situation. The mean, right? What would we expect to see values to expect to happen? How many households, if 25% of the households were wireless and we asked 20 households, on average, how many households would we expect to be wireless? And then also, what's the standard deviation of those distributions look like? So in this case, the mean is just n times p. 20 households times 25%. That's how many we would expect on average to see. And then we also have a standard deviation formula, which is actually easily calculated. It's n times p times 1 minus p. And so then we have those values right there. And so from there we can then go ahead and then answer some questions. So finding the mean and standard deviation of a binomial random variable. Those are easily applicable formulas according to, and we do need to do these by hand. StatCrunch does not do these calculations for us. I think we might be able to, actually now I think about it, we might be able to fake it in to do it, but there's no command to do that. And so here is how we would calculate it. So you do need a calculator. Here's our information. So in a random sample of 300 households, determine the mean standard deviation number of wireless households. So if we ask 300 households and we know 25% of them of households, but we sample 300, how many would we expect on average to see? It would just be 300 times 0.25. And so then that would be our average, what we see. And so in this case, what is 25% of 300? 10% is 30, 60, 15. So this turns out to be 75 households. And so then how about the standard deviation of the random variable? This would just be the square root of 300 times 0.25 times 0.75. That's the complement. 1 minus p, 25. 1 minus 25 is 75. And so in this case, the standard deviation, that's the population standard deviation, is what we get here. So if you type this in correctly, you get a value of 7.5, which is just coincidental with the 75%, 7.5 households would be the standard deviation. Now, an important question is, like, why do we care about those values? Well, one way we apply standard deviation and mean is through this question. How do we determine if something is unusual? If you observe something in a binomial experiment, is that unusual what we just saw? Is the value we got for that probability, is that something we would expect to see, or do we say that's unusual? And so in order to kind of determine that, we use what's called the empirical rule to do that. And so what we're looking at when we look at the empirical rule, which we already have learned before, one thing we learn from the empirical rule is that 95% of the observations lie within 2 standard deviations of the mean. And what becomes important later on, we do this, but I'll bring it up now, is what we learn is that there's a rule of thumb. In order for us to kind of apply the mean and standard deviation, the probability distribution will be needs to be bell-shaped. That's how we use the empirical rule when we do the calculations and look at the different values. And how do we know if it's going to be bell-shaped? If it passes this test, n times p times 1 minus p. If it's greater than 10, then the probability distribution will be bell-shaped. And then if that's the case, then we can apply the empirical rule to that. And so looking at your notes here, explain if you determine if observation is unusual. What we have to first know is we need to know that the probability distribution is bell-shaped. We need to know that. And in order to know that, that only happens if n times p times 1 minus p is greater than or equal to 10. So we need to check that. If that's the case, then we can apply empirical rule. We apply the empirical rule that says that 95% of all observations lie within 2 standard deviations of the mean, which you guys know already. What you guys already know of the mean. And so what does that result for us? How do we then determine that? I think we're squeezing it right here. What we then know is that any observation that lies outside of 2 standard deviations is unusual. And the note we use is this here. Our kind of fences for that are 2. I don't use the word fence. Are the mean minus 2 standard deviations and the mean plus 2 standard deviations. Those become kind of the interval, kind of the values that we end up checking right there. And so we'll do one right now on this problem here. And so on this problem here, we have 75 and 7.5 here. So according to this information that we just had, we know the mean from up above. The mean of that variable was 75. The standard deviation was 7.5. And so then we have these values here, and it's kind of like outliers. We have these, we don't call them fences though. And so we have the mean is in the middle. There's your 75. And then we have 1 standard deviation and 2 standard deviations. We've done this before. 7.5, so that's going to be 82.5, and this is going to be 90. This would be 67.5, and this is 60. And so what we know is any value. Where's 92? 92 is right there. And so because 92 is more than 92 is unusual, since it is more than 2 standard deviations above the mean. And so now we know it's unusual. And how did I get those values again? Well, these are kind of the values there. 75 plus 2 times 7.5 equals 90. And then we have 75 minus 2 times 7.5 equals 60. Those become kind of the 2 standard deviation mark. And so 92 is unusual.